had a function and you had a direction. Hold on one sec. Hold on. Oh, right. This is that Henry. Okay, so directional derivative here. It's a little hard to see. Someone can pull on the shades. That might help a little bit. You'll notice that what do we have here? The first thing we do is we make sure we unitize the vector, and then we have the u1 component and the u2 component. Directional derivative is going to be a scalar value, correct? It's a rate of change in direction. What you end up with is, oh, that's what you're leaving. Oh, I'm really sorry. I thought you were just like randomly like refolding your jacket for fun. I was confused. I was like, please sit and join us. Have fun. Nice. Nice. He's got a children's performance thing, you know. I don't want to walk myself into things and get it on record. So what you end up with is, you'll notice that this follows the form of a dot product between two vectors. First vector being fxab, fyab, and the second vector being u1, u2. So you can pull this apart. You can pull this apart and turn it into an f at a point ab is the partial with respect to x, I, and the partial with respect to y, j. This just tends to come up with this definition is what they like writing. So basically what you're seeing is mathematicians will see something repeated over and over again, so they'll give it a special name. That's all that's going on here. There's nothing like too incredibly new here. So in a really straightforward fashion, they ask for find the gradient vector find the gradient vector of f of xy equals x plus ey at point 1, 1. At point 1, 1. So what would you do if you wanted to do that? How would you go about doing that? And remember, it's a vector, right? So what's it going to be? I plus ej. Yeah, that's it. That's it. So just numerically, generally they get easier, right? Generally speaking, they get easier. So let's take a look at this sentence here. So what does the gradient vector tell us? So we now know that the directional derivative in the u direction is equal to the gradient of f dot u. That's just reassembling what we already knew with notation that we already learned. This enables us to see what the gradient vector represents. So here's the idea. If you have a directional derivative u, so this vector right here, see that vector right there? Can you see me drawing on there? That vector is u, and this right here is another direction. So that's the direction of the gradient vector right there. This is the direction. This is the gradient vector. Okay. So you have your gradient vector and you have u. Okay. So just I'm labeling them as grad f and u. So we have this interesting relationship here. We know that the directional derivative, the rate of change in the the rate of change in the u direction, we already defined it like this. Remember, we just disassembled it, right? But what do we know about the dot products of two vectors? What was one of our original definitions for dot product of two vectors? The magnitude of the first times the magnitude of the second times what? Cosine theta. What's the magnitude here? It's 1. So now what we can state, all we're doing is restating what we know. We now know that the directional derivative in the u direction is going to be equal to the magnitude of the gradient of f times what? Cosine theta. Does everybody understand this so far? All we've done is rearrange what we already knew. We're not just a project. Okay. Yes. So here's the thing. You see the circle around here? Let's say we fixed our gradient vector this way. So here's our gradient vector. And let's say we move the u, or you can do it vice versa here. It's fine. But let's say we fix the gradient vector here. If the degree angle is 90 degrees, what does that tell us? What? What's cosine of 90? 0, right? So we know this because the dot product of the vectors, if the dot product is 0, you know that they are perpendicular, and that's because of this right here, this definition, correct? So here's the deal. If the direction is perpendicular to the gradient vector, what's it always going to come out to be? 0. So let's go to the other side of this. If we wanted to maximize the value of the directional derivative, what do we want theta to be? None. We want this to be what? 1. We want this to be, what's the largest value cosine can be? 1. The magnitude of the gradient never changes, right? That's static. The only value here that changes, the overall value of the directional derivative is going to be theta. Cosine theta, right? The largest value cosine theta can be is what? 1. So if we want to maximize the directional derivative, we want cosine theta to be 0. So to maximize the directional derivative, we go in the same direction as the gradient. The gradient. They're both going in the same direction. So you can either think of it as this is fixed or this is fixed. It's functionally the same thing. The idea here is, just remember, we know that the directional derivative is the dot product of these two, correct? The dot product of these two is the magnitude times cosine theta. This is 1, because by definition it's a unit vector. So what are we left with? The magnitude of the gradient vector times cosine of theta. If you have a given function, the gradient vector is what it is. You take, remember what the gradient, we defined it up above, it's f of x at the point, f of y at the point. So this magnitude is static, right? The only way you therefore change the magnitude or the overall value, scalar value of the directional derivative is to change the theta value. So how do you maximize the theta value? You go in the same direction. You go in the same direction. What this tells you functionally is this. The steepest path is the gradient vector. The steepest path is in the direction of the gradient vector. You kind of with me so far? Yesterday, or sorry, last class, there was, we talked about, so what we're going to get, so if you have a contour diagram right here, another way to think about this, so let's say you had a contour diagram right here. So let's say this was 5, and then 10, and then 20, and then 30, right here. Let's say you were at this point right here. Generally speaking, if I asked you, and again, you don't know what the function is, if I asked you, what's the steepest path you could take?
Depends on the shortest distance.
The shortest distance to the next contour line. Exactly, right? So if we had a function for this, you could find it exactly. But if I asked you, if I said, here's this point, point me in the direction of the steepest path, it would be this way, right? It would be the shortest distance. It wouldn't be something like that because that's longer, right? The idea, though, is this right here, what we've just shown, this direction is the what vector?
Gradient.
It's going to go in the same direction as the gradient vector.
Why wouldn't you go left?
Ah, exactly. So what's the difference between speed and velocity?
Oh, it's absolutely. You said the steepest.
I understand. So again, I'm getting to the punchline. What's the difference between speed and velocity?
Scalar vector.
There's one's a scalar, one's a vector, right? So in certain circumstances, when you do this out, one direction, either forward or backward, will work. Sometimes both of them will work depending on the even spacing. So here, can you eyeball this distance? It's a little hard, right? Do you understand? Like if this one was closer,
just go down
but I could also specify you're trying to go up the mountain, right? Okay. You understand what I mean? There's just a slight difference. There's like all I want you to get out of this is the gradient vector is the direction of the steepest path. You with me so far? You'll also notice that Jesse.
Oh, sorry, I'm actually still putting it.
Okay, I'm asking you. We're gonna walk through this together right now. So fx xy. So the directional derivative. So what's it gonna be?
It's gonna be 1.
1, correct. Similar to what we just did before. F of y xy. What's that gonna be? What is e to the y, exactly. So then what is fx at, what point are we at here? 1, 1, right? What is it? It's going to be 1. And fy at 1, 1 is going to be what? E. Anybody have the other ones at all? So let's say v2 is, what's one of the other vectors? One of the other vectors is I plus 2j. Anybody have that one for me? What's f, and so what is fu2 going to be? Anybody have it for this one? Yeah, what do you get? Yeah?
It's going to be 1 over the square root of 5 plus 2 over the square root of 5.
Can you give me the decimal? I want decimal to 3 decimal places. That's what I want. 2.78.
2.878.
879 or 878, depending on how you truncate. And v3? 2.89 what? 95. FU3, right there. Good. So here's the thing. So negative, positive, positive. Now, you would make it. You know that fu at 1, 1 has to be less than or equal to the magnitude of the, of what? If cosine, remember what?
Magnitude
of the grad of f, exactly. because you know that the directional derivative is that times cosine theta. Cosine theta maxes out at 1, so you know that the direct. Well, if you wanted the maximum, right? So if you wanted the maximum of this, you just do the magnitude. And what is it in this case? It's right. Where is it?
1.
It's I. You know, we know that grad of f is I plus what? Ej, right? So the magnitude of that is going to be the square root of 1 squared plus e squared, right? Can someone do that for me and just tell me what that is? I have it right here, I think. It is. Someone do that for me. 2.896. So does that do our answers, are they under that value? Yeah.